Alright, so after my last video on gyroscopes and gyroscopic navigation and such, got a lot of good feedback on that. It's really opened up all kinds of avenues to explore further. Lots of different tangents where you can go from that and look into deeper. So one of the tangents that I've been looking at lately involves the use of gyroscopes and what's called inertial navigation systems on ICBMs, intercontinental ballistic missiles, of course. So, which is interesting because as I've been learning more about not just gyroscopes, but how gyroscopes are used in combination with other elements to make up what they call the inertial navigation systems. It's just been really interesting to see how that all plays together. Now, when you're looking at something like, ICBMs and nuclear warheads and all that, obviously the more recent technology you're trying to look at, the more difficult it's going to be in terms of, the more likely it's going to be classified. So once again, like with the previous video, I've kind of found that when you start going further back into time and looking at the older stuff, the stuff that was first coming out when NASA was first coming into existence, that's when I think it's in some ways easiest to look at a lot of these concepts and a lot of these questions, because it isn't being obscured by so much of the modern, just the complications where, of course, the naysayers are going to fall back on just explaining it away with, modern computers and satellites and all these things. When you go back to things like the Atlas rockets, which I've been kind of focusing in on lately, it's so interesting because obviously when you're looking at the late 50s, early 60s, there was no onboard computer systems, not like at all like we have today. They were incredibly basic. There was no satellites because these are the first rockets that were used to even start putting satellites up there, supposedly. So you're really just reducing it down to sort of the most basic elements, and so once again, when you're looking at this concept of using the gyroscope to navigate, or to navigate and to understand, to maintain fixed position and understand how far you've traveled in relation to that original position. And I was talking about it in the last video in relation to ships and planes and things like that. Now, if there's any application of a gyroscopic navigation system or an inertial navigation system that you would think would just absolutely have to account for the curvature of the Earth, it would be an intercontinental ballistic missile, because they're going faster than any plane or ship, obviously, and they're going such huge distances around the globe. I mean, curvature would be a huge issue, obviously. And it's just amazing as I've been looking into, just reading about the Atlas program and how it all progressed, and learning about delta V and all these different kinds of calculations. It's interesting to just see like how they try and explain a lot of these things, where they talk about it's called suborbital, and how basically they explain it as that these rockets, that the Atlas rocket is supposedly had a maximum range of 9,000 miles, which is pretty crazy when you think about if the circumference of the globe is supposedly somewhere around 24,000 miles. 9,000 miles, you're talking, that's a little over 1/3 of the way around the ball. Now that's a lot of curvature. And so basically these things go up, and they call them suborbital trajectories, right? They say that they're not going into orbit because technically they're not going all the way around the globe. So that's a suborbit, right? It doesn't go all the way around, but they're going high enough They're going much higher than even what we would call low Earth orbit. So they're technically going into space, and yet they don't ever talk about, using the same principles as that supposedly spacecraft and satellites use to hold orbit as they go around the ball. So they just use these parabolic type equations, and yet they go up, they bank, and then they would have to hug the ball for the majority of the flight before they started to drop back down. So the more you look at it, the more just bizarre it becomes. Now I found a couple of clips here. The first one is from a spokesman for, I believe, what is the Convair Corporation, which was a subcontractor that was assigned to build the Atlas rockets. I think they were built in San Diego and then launched in Florida. So he's explained. He talks for a while about the history of the Atlas rocket, but in this part he's talking about the navigation systems, and that was the part I was most interested in hearing, because I wanted to see if in fact there was any explanation given, especially in these early Atlas rockets and such, for how gyroscopes or inertial navigation systems, which apparently use not just gyroscopes but something called accelerometers, which actually measure acceleration and speed in any given direction. How are those two systems which work together, how are they going to accommodate for the curve? How is this supposedly going to continually correct, as that other video says that the jet planes did? How is it going to correct the gyroscopes as it's flying at hundreds of miles an hour around the ball, right? Because it would have to be correcting pretty darn quickly as it's moving that fast. So I was curious to see if I could find it mention that anywhere, and so far I've not found anything explaining how this type of navigational system used on a rocket would have to make that kind of adjustment. So here it is.
In operation, all the Atlas engines are started on the launcher, and the missile is held down in order to be sure that the engines are operating properly. After this is determined, the launcher releases the missile, and Atlas takes off vertically, propelled by rocket engines made by the Rocketdyne Division of North American Aviation. It continues to go upward vertically for about 10 or 12 seconds, during which time the missile rolls about its vertical axis in order to establish the target azimuth plane. The missile programmer then commands a zero gravity turn in the direction of the target. The missile continues in first stage operation under control of the missile autopilot. After about 2.5 minutes, the guidance system commands the booster engines to shut down, and these engines, together with the booster section, are jettisoned and fall away. The Atlas then continues under the operation of its sustainer engine and the two small vernier engines, which provide roll control during second stage of the flight. The missile is guided during second stage by the ground radio guidance system furnished by the General Electric Company. After about another 2.5 minutes, the sustainer engine is shut down, and the vernier engines are used to make a final velocity adjustment for the missile. Then, the reentry vehicle is unlatched. Small solid propellant rockets in the main Atlas tank move the tank away from the reentry vehicle, and it continues on its way to the target without further guidance. It takes about 30 minutes for the reentry vehicle to reach the target.
The inertial guidance essentially was a stabilized platform. That just means gyros would stabilize a three-axis gimbal. Physically, something reasonably sized that you get in a missile. And mounted on there were two accelerometers Accelerometers were such that they had a internal motor. One was pitch and the other was yaw. If you shot your weapon like an arrow, and GE Syracuse developed the Doppler radar, that you could get the velocity of the missile with the accuracy needed for the targeting. You could get the exact velocity of this object when it has no more energy and it's floating through space. It's inertial. And any forces that would act on the body other than just free fall, it's like being in gravity-free fall, would be measured by this system, accelerometers. And if you were buffeted off course, say on re-entry, and you get a wind shift, and it blew the missile off its destined path, you could measure in feet, as we did, and with the analogy, there's so many feet to the left of your target, or you're short of range. You'd have to pitch up. You're in a glide path now. So that if you're not on target, the inertial system picked up how far you were off, or how far, what range you were off. And it had, in effect, dead stick wings that would fly, and once you come back into the atmosphere, would try to flatten out the missile to reach further, and also to steer out all these errors that you accumulated.
Okay, so he mentioned that the accelerometers, and it's interesting too. That's kind of a whole nother conversation in itself. Maybe another video is warranted for that. But basically what I've been learning about accelerometers is that they measure acceleration, obviously, and speed, but they use it by measuring against the pull of gravity. So without, I mean, you can go on Wikipedia and it'll tell you point blank that accelerometers don't work at all without gravity, which is even more interesting when you think about they're a part of the inertial guidance system on missiles and rockets that are going up and out of the atmosphere or into the outer atmosphere and going hundreds of miles over the earth, and supposedly in ranges which, you know, things like space stations and satellites are dealing with reduced gravity, and wouldn't that just throw off your entire system? But even beyond that, it seems like the same type of inertial navigation system is what they use to supposedly go to the moon, which is crazy because if you're if you're leaving the Earth's atmosphere altogether and just floating out in the complete vacuum of space, then obviously an accelerometer is completely worthless, and not to mention your gyroscope is pretty much completely worthless. And so yeah, I'm kind of curious to see how they'd explain that one, especially because, you know, when you get to things like Apollo 8 on that mission, when they're going around the dark side of the moon, you've got no radio contact, no radar contact, a gyroscope that is useless, accelerometers that are useless. You have what sort of guidance system could they possibly have used for Apollo 8 to go around the quote-unquote dark side of the moon and be able to navigate and have any idea of where they were in space in relation to the Earth, the moon, or anything else? They would have been flying completely blind. So I'll keep you posted, and let me know if you guys are researching any of the same sorts of things. So it's really opened up all kinds of avenues to explore further. Lots of different tangents where you can go from that and look into deeper. So one of the tangents that I've been looking at lately involves the use of gyroscopes.
Roger. Radar go. Door map started. Go map go. Beacon started. Beacon go. JTO. JTO, go. Telemetering trailer, quality. Go. Telemetering range ready. Telemetry, go.
Are used in combination with other elements to make up what they call the inertial navigation systems. It's just been really interesting to see how that all plays together. Now, when you're looking at something like, ICBMs and nuclear warheads and all that, Alright, so after my last video on gyroscopes and gyroscopic navigation and such, got a lot of good feedback on that, and what's called inertial navigation systems on ICBMs, intercontinental ballistic missiles, of course. So, which is interesting because as I've been learning more about not just gyroscopes, but how gyroscopes